Dear Professor, so today I'm presenting my research project titled The Interconnected Relationship Between Machine Learning and Database System. This is a comparative platform study and design perspective. So this is today's table of contents. So, to begin with, let's clarify the core motivation behind this study. Machine learning allows systems to improve their performance over time by learning from data without being explicitly programmed. But success in machine learning doesn't rely solely on sophisticated algorithms. According to Dominguez, machine learning has already transformed sectors like search engines, fraud detections, and recommendation systems. However, what makes those applications effective is not just the models, but the data infrastructure behind them. Scalable, high quality, and well managed data is the foundation of reliable machine learning systems. Then in 2016, Zaharia and other authors highlighted a major limitation. Traditional relational databases often fall short in supporting machine learning growing data demands, especially with unstructured and high velocity data. This gap led to the rise of NoSQL databases, data lakes, and ML orchestration tools like MLflow, designed to automate and scale the complex pipelines. So, to frame the study, we need to understand what machine learning is and what it relies on. Machine learning enables systems to detect patterns to improve without being explicitly programmed. It's widely used in domains like fraud detection, recommendation system, and natural language processing. But algorithms alone aren't enough. As Dominguez in 2012 said, garbage in, garbage out. Machine learning performance depends heavily on data quality, not just the quantity. So there are three main machine learning algorithms. But firstly, supervised learning uses labeled data. The second one is unsupervised learning, finds hidden patterns. And lastly is reinforcement learning, learns via feedback and rewards. These techniques depend on reliable data infrastructure. Traditional relational databases often fail to meet modern machine learning demands, especially with unstructured or fast changing data. This has led to the rise of NoSQL systems, data lakes, and tools like MLflow, which support the full machine learning lifecycle from reprocessing to versioning. And because of the concept trips, machine learning system must continuously monitor, retrain, and adapt, making interaction with database system not optional but essential. This forms the technical foundation for the rest of the study. So now let's understand about the interconnected roles of machine learning and DBMS. The relationship between machine learning and data system is not just complementary, it's interdependent. Machine learning model needs structured and unstructured data in real time, while databases must now support model training, inference, and monitoring. This slide highlights the shift from treating data storage as passive to recognizing DBMS as an active layer in machine learning pipelines. This is essential for enabling continuous learning, lifecycle tracking, and performance tuning. Without this linearity, machine learning deployments remain siloed and inefficient. So, moving into architectural evolutions, this timeline shows how machine learning workflow have evolved. We move from ETL, where transformation happened before loading, to ELT, which is better suited to cloud-native storage system. Then came orchestration tools like MLflow that brought modularity and automation. Now we see in database ML and lifecycle automation where model trains continuously. Each stage reflects growing architectural maturity and shrinking separation between storage, processing, and learning. This is not a linear upgrade, it's a fundamental shift in how systems are designed. So, we need These workflow changes is a deeper infrastructure shift from relational databases to NoSQL systems, and now to cloud-native machine learning platforms. RDBMS offers consistency but lack flexibility. NoSQL addressed data diversity but introduced the governance issues. Cloud-native machine learning pipelines aim to resolve both integrating data storage, transformation training, and deployment under one scalable architecture. This visual supports the argument that machine learning DBMS integration must be addressed at both the pipeline and platform level. So, this slide highlights the five key challenges in integrating machine learning with DBMS and the corresponding solution proposed in my research. Firstly, data movement slows performance and raises security risks. Federated learning addresses this by keeping data local during training, especially useful in privacy-sensitive sectors like healthcare. Model versioning is inconsistent across tools. Standardized APIs and registries improve tracking and reproducibility. Restore contention between machine learning training and database workloads impacts performance. Hybrid architectures that separate inference from training help improve reliability. Tool fragmentations makes end-to-end automation difficult. We need unified ML lifecycle platform that integrate data and model pipeline. Privacy and compliance concerns persist. Embedding privacy preserving computation like differential privacy within DBMS help mitigate legal and ethical risks. These are not isolated problems, and solutions shouldn't be either. That's why I propose an integrated architectural approach, which I will explain in the next slide. So this table presents a side-by-side comparison of these leading machine learning integrated DBMS platforms based on both technical documentation and academic evaluations. Let's start with Google BigQuery and Vertex AI. This is a serverless architecture, which means infrastructure management is abstracted away. It supports tight ELT integration and O2ML pipelines, making it easy to launch model weekly. However, the trade-off is lower flexibility and control. Its complex pricing and limited customization can be challenging for advanced users or teams that require fine-grained tuning. Next, Databricks and MLflow is built on a lakehouse architecture using Delta Lake. It stands out for its customizable Spark-based workflows. It offers strong support for model tracking and reproducibility, but with higher setup and management overhead, this makes it more suited for teams with engineering capacity and want full control over the ML lifecycle. Finally, Amazon Redshift and SageMaker deliver a highly integrated AWS experience, particularly useful for organizations already useful in the AWS ecosystem. It supports real-time model monitoring and deep integration with services like Lambda and Step functions. However, it comes with risk of vendor lock-in and operational costs can escalate at a system scale. What this comparison makes clear is that no platform is perfect. It prioritizes different architectural dimensions, whether that's simplicity, control, or full stack integration. These insights inform the later architecture I propose next, which aim to combine the strengths of the platform while addressing their limitation through a modular, decoupled design. So to address the platform trade-offs we discussed, I designed the layered architecture to support the scalable and lifecycle-aware ML-DBMS integration. It includes the four key layers. The first one, data storage layer, manages structured and unstructured data using platforms like BigQuery, Delta Lake, and Redshift. It forms the foundation for all upstream ML operations. The second one is machine learning services layer, handle training, experience tracking via tools like Vertex AI, MLflow, and SageMaker. Support both Ultra ML and custom models. The third one is Pylon's orchestration layer. Let's connect data and models using ELT workflow, CI/CD system, and versioning tool to ensure automation and reproducibility. The fourth one is deployment and monitoring layer. Enable real-time inference, performance monitoring, and feedback loops to continuous learning and compliance. So why it matters? Rather than treating tools as isolated solution, deep model align them architecturally, addressing critical challenges like latency, reproducibility, and governance, challenges that no single platform solves on its own. So to conclude, the integration of machine learning and database system is essential for building a scalable data-driven applications. Machine learning success depends not only on algorithms but also on robust, well-governed, and high-quality data infrastructure. Solutions like federated learning, OutML, and hybrid architecture address critical integration challenges, especially around privacy, performance, and complexity. Continued progress will require standardized framework and cloud-native architecture to align DBMS and ML workflows. Future systems must be scalable, reproducible, and ethically aligned, embedding machine learning directly into the data ecosystem. So for future direction, federated learning trains model locally across decentralized data without sharing raw data, and it enhances privacy and compliance with data protection laws. And the second one is the AutoML. It's automate model selection and tuning, make machine learning accessible to non-experts and accelerate deployments. And the third one is standardization and reproducibility. Unified APIs and lifecycle tools are key to consistency, governance, and scalability. And last one is cloud native architectures. Embed ML directly in data DBMS platform to reduce latency, enable real-time inference, and support continuous learning. So that's all for today's research. Please let me know if you have any question. And this is the list of preferences. So thank you for your listening.